Hello. So welcome to this tutorial uh, on the design of a 4-bit binary adder using behavioral model Verilog coding. So in this tutorial, we are going to use this Xilinx software to simulate this 4-bit binary adder, which we will make using behavioral modeling, right? So I've already made the project. So let's add a source file. So since we are going to use the Verilog coding, so select Verilog module and then specify a name. So let's call it adder 1-bit, right? So in this tutorial, first we will make a behavioral model uh, of a 1-bit uh, uh, adder or a full adder, and then we will extend that concept to 4-bit addition, right? So let's click next. So so uh, and then click next, and then click finish. So now here we can write our code. So so as we know, we will specify the inputs, the list of inputs and output in the within these brackets. So in a 1-bit adder or full adder, there are two outputs: sum and carry. So S and C are the sum and carries of this 1-bit adder, and A and B are the inputs, and C in is the carry in, right? So let it be C, and then let this be C out, right? So now we know that these are the inputs and these are the outputs, but this software or this system, it does not know that. So we need to specify which one of these are inputs and which one of these are outputs. So we do that using this keyword input, and we write A, B, and C. So now our compiler or this Xilinx software will through this command, it will know that A and B and C are uh, inputs, and so we specify outputs using this output keyword. So right, so now we have specified inputs and outputs, uh, a behavioral model of 1-bit adder. So as we know, in behavioral modeling, we do not implement the circuit, right? So we only implement or we only specify the behavior of the operation, right? So addition, it's very simple. We perform addition using this uh, operator A plus B. So we are adding two bits A and B. So we can add these two bits using this operator plus operator, right? And so we have a third bit as well. So we will use another operator. Uh, so now we have this addition of 3 bits, which we call a full addition. And so now we need to specify the output of this operation. So we know generally when we add 2 bits or two or more than 2 bits, the output is generally in is generally in more than 1 bits, right? So typically when we add 3 bits, uh, output is in 2 bits, right? So we have a carry, so we have this C out, and we have this sum, right? So the so this is how we specify the output of this operation. So this means if we have an operation that is operating on 1-bit variables, but the output of the operation is more than 1 bit, then we are going to use these brackets to specify those outputs. So C out is the bit that uh, contains the bit and in the twos place, and this S or the sum is the bit that contains the bit in the output at the units place, right? So now once we have specified this, so uh, uh, if we want to assign this output of this operation to these two variables, Then we need to write this assign statement here. So now this is the behavioral model of a full adder. So let's simulate it. So let's first click on the simulation and then click on this uh, in this file name, and then here click on this plus sign and then click on this behavioral model. So it's asking us to save this. So let's save it, and as you can see, uh, it is working fine. So there are no errors. So let's make a test bench. So now let's add another source file. So this time it should be a Verilog text fixture. So let's name it tb underscore adder 1 bit, right? So next, so select this file because we need to link this module with the test bench. So now once you click this next and this finish, so you see the inputs and outputs already defined along with the call to the module. So this is the call to the module, and these are the definition of the inputs and output. And as you can see, we define the inputs using reg command uh, because we want to dif, we want to change the value during the execution of the program. So so now let's give the input combination. So it's so let's make a truth table. So let this be 000 and make it 001 and 010 011 100 101, and then we have 110. So you just need to uh, copy and paste and change the values, right? So that's it. So this is our truth table, and let's just write this finish command, and there it is. So now let's save it, click on the file and check for errors. So once there are no errors, behavioral check is okay. So then now it's time to simulate it. All right. So as you can see, it is letting us know that simulation is done, and it is done within 800 nanoseconds. So you just need to click on this window default.wcfg, and now as you can see, simulation is done within 800 nanoseconds. This is because we have used this finish command after uh, 800 nanoseconds. So every time we have used 100 nanosecond delay, it is added, and it culminates at 800 nanoseconds, right? So right. So let's go back to the simulation. So now here, click on this fit to screen, and as you can see, uh, this is the result of the summation, right? So now let's go back to this file, right? So as we know, we use this always block uh, to write behavioral model coding. So we have not done that. As you can see, we only use this signed statement, and that's how we did it. But generally, we use this always block. So let's add this always block, because when we extend it to 4-bit addition, we will need this block, right? So in always block, we specify inputs as the conditions of execution. So we have 3 inputs. So we will use all three inputs as the condition of execution of this block. And since we have only one command, so we are not going to use the begin and end statement of this block. So because generally if you have only one statement, so you do not need to use the begin and end statement, right? So now once you have defined it using the always block, you do not use this assign statement in the always block. Instead you define the output as reg type, and once you define this output as reg type, uh, the you do not need to use this assignment statement, right? So we do not use the assign statement. Otherwise, if you use this assign statement, let me use this assign statement and see what happens, right? So let's save it, and so let's run its behavioral check, and as you can see, we have run into errors, right? So it says procedural assignment to a non-register cout is not uh, permitted, right? So so let's remove this assign statement, and we can define this as reg type. And once we define this as reg type, now in always block we can use this equal to sign as assignment statement. We do not need to use this keyword assign, right? So now let's save it, and as you can see, it will be fine. Yeah, it's perfect. So no errors. Now again, uh, let's run its test bench. So we click rerun. So this one is the behavioral check for the test bench, and now we simulate it. And so this generally you encounter this error because there is another simulation running. So you need to close this one. So let's close this one, and now you click on this now if you click on this simulate behavioral model, so this will not you will not get any window. So once so if this happens, you just right click on it and click rerun all. So here we are, we click on this default.wcfg and click on this screen to fit, and as you can see, this is the result, right? So now let's extend this idea to 4-bit uh, binary addition. So I've already added this file where I'm going to write this 4-bit binary addition behavioral code, right? So behavioral Verilog code to be specific. So before we write this code, let me show you how this 4-bit binary addition works, right? So in this addition, just if you look at the selected area, so I've shown you how we add two 4-bit numbers. So here A and B are the two 4-bit binary numbers. C are the carries from the previous additions. So since in the first addition, uh, so there is no carry, no addition prior to this. So this carry in this addition is 0, right? But in the next addition, when we add A1 or the bit in number A at location 1 with the bit in number B at location 1, in that case we have this carry from the previous addition, and that previous addition is this one, right? So the C1 is basically carry from this addition, right? And similarly in the next addition, when we add the bits in A at location 2 to the bit in B at location 2, we have this carry C2, and this carry is basically the carry from this addition, right? So as you can see, we need to mimic. So we have already made a behavioral model of this 1-bit addition, which could be any one of these. So in order to make a 4-bit binary adder, we need to mimic that this 1-bit addition 4 times, right? So so let's go back to this 1 bit adder and let's copy this text. Since we have already made this this module, let's use it to our advantage, right? Okay, so now we have two 4-bit numbers a and b. So let's define a and b as inputs, a, b, and we have this sum s, which is a 4-bit sum, as you can see here, right? So let's define a and b to be two 4-bit inputs. So this we define like this. So if we want to define a 4-bit variable, we specify these locations. So we say that the location of this number, this these numbers a and b have 4 bits, and where each of these bits have locations 3, 2, 1, and 0, right? So bits at these locations, right? Okay, and then we specify this output, and since output in this case is in fact s sum is has generally has 5 bits, and that is because this s4, let me write it here, s4 is generally the bit from the final carry, that is c4. So c4 is generally also part of the sum, right? So let me write it here, c4. So instead of, yeah, so I think this will make more sense, although now I need to move this here to make more sense of it, and here and here, and I need to write a 0, 0, and a 0 here, right? I guess this will now make more sense, right? So this is c4, right? So this is how our sum is calculated. Let me remove this. So as you can see, the sum has 5 bits. So let's define this as a 5-bit variable, 5 colon 0, sorry, 4 colon 0, right? So this so now once we have defined this input and output, so we can take this. So the carry, as you can see, this we do not need to define this c as an input, because we can define them as wires or registers, because these are intermediate wires or connections, right? So let me define this reg type cout comma cn, right? So now let's move within this always block. So so now we need to write the code that adds uh, a naught and b naught, or this a0 or b0, and places the sum in s0. This is the code that we need to write first. So let's do that. So we add a0 with b0. So it's very simple. You just need to specify the location of the bit that you want to add. So in this case, we want to add a0 uh, with in fact a0 with this b0, and in this case cn is 0. So we need to specify that cn is 0. So it is basically 0, right? So so this is how, and we need to place the sum of a0 and b0 in s0, right? So we need to specify the location for the sum, and we can keep this carry in the cout, and we can use this in the next edition, that is in this edition, right? So we need to copy this. So now, as you can see, we have written a multiple line code. So whenever you write a multiple line code within this always block, it is important to write this begin block, begin and end statements of this block, right? So now you can write the multiple line code within this block. All right, so now you just need to copy this and paste it here. So now we need to add this A1 and B1 and place the sum in S1, right? And in this case, the carry is the carry from the previous edition, right? So first of all, let's assign the C out, the carry from the previous edition, to C in, which is the carry in this next edition, right? So you replace the value of previous input carry with the next input carry, right? So and now you since you are adding A1 and B1, so you change the index, right? And so you can just now do the same for the next bit additions, right? So now you need to add C2, sorry, B2 with A2 and place the sum in S2, and similarly you do the same for uh, B3 and A3 and place the sum in S3, right? So this is the 4-bit sum, but you know there is one more addition that is still left. So it is exactly not an addition. It is basically you need to assign this C4 to the location S4, right? So write S4 equals to C4, right? Right. So in fact, Cout. So in this case, Cout is now the output from the latest edition, which is the edition between A3 and B3, right? Right. So this is how we can make a 4-bit behavioral model. Uh, behavioral model of a 4-bit binary adder. Now you need to run this. So we need to remove the C here because we have only 2 inputs. So we specify the inputs here. And so since we copied this from the previous file where we had this third input C, so it is important that we remove it from here, right? So now you save this file and run its uh, click on simulation, click on the file and run its behavioral check. So you will see this is perfectly fine. There are no errors. So now you need to write its test bench. So make a new source, write the name tb underscore adder 4-bit, and then click next. Specify that you want to make this test bench for adder 4-bit, so you want to link this adder to your test bench, and now you will get this window. So now this has already defined the inputs and outputs. You just need to give the input combination. So this A is not a 1-bit number, it is basically a 4-bit number. So you specify 4 single quote B, and so this is how you define a binary number. Yeah, so 1010, right? So so in order to define a binary number, you first specify number of bits, and then you specify type, and in between you have this single quote, right? Okay, so you can do the same here. You need another 4-bit number, so you can copy it here and then maybe change few things. So maybe we want to make it 1010, right? So these are the 2 4-bit numbers that we want to add first, and then we would want to add. So you can have any type of test bench. You can assign any 2 binary numbers. So I'm assigning another binary number that is 9 and 7, right? Okay, so now I want to save this. You can, if you want to add more binary numbers, like more combinations of binary numbers, then you can maybe have a few more instances, but in this case this is it. So let's now simulate it. So click on this file and then simulate it, and as you can see there are no errors. Now let's click on the simulate behavioral model, and so here we are, and now you click on this and there it is. So when you are adding 1010 to 0101, the sum is 0111. So sum is all ones in the 4 bits for the first 4 bits, and since there is no output carry, so fifth bit is 0. But in this case we are adding 9 in 7, so in this case we have this sum, that is 16, right? So this is the binary of 16. So as you can see, 1 plus 1 is 0, 0 plus 1 is 1, but since we have a carry from the previous addition, we will again have 0, and similarly we can keep on having zeros until the uh, the final carry arrives, and that is 1, right? So this is your 4-bit binary adder, right? So let's go back and write this finish statement here, right? So now let's save it again and maybe check its behavioral model again, and now you run its behavioral model. So it's saying that you have already a simulation open. So let's close this one. You can close this one, and then you can, now if you click on it you will not get this window. So in this case now you need to right click and rerun all. Right, so just click on this default and you will see, so these are your summations. So this is the first summation and this is the second summation, and now there is so the simulation finishes within 200 nanoseconds, right? So um, so now we have simulated the 4-bit binary adder module that we just made, which is this one. So but this as you can see in this module, this statement is repeating 4 times. So if you want to make uh, maybe an 8-bit adder, in this case this statement will be repeating 8 times, and if you want to go on more than 8 bits, then this statement will be repeating more times, right? So so there is a better way to do this. So let's use this for statement, for loop statement, right? So you specify I is equal to 0 and semicolon, I is less than 4, so semicolon I plus plus. Right, so we cannot use this I plus plus here. We can do this increment like this, right? So this is how we use this for statement, right? This begin block, begin for block, and end, right? Right, so maybe we can write this end here. In fact, we do not need all 3 of these statements. We just need one of these, and you can take this one out because this is only one time, only a one time uh, declaration, right, for initialization. Okay, so now you just need to, first you need to specify that this I variable is an integer I, and now you just need to write this uh, I here, which is an index that is going from 0 to 3. So it is going from 0 to 3 based on this statement. So right, so you need to specify C in, which is in this case is since we are first computing this sum, and then you can specify C in here, because C for the first time you've already specified that C in is 0, but for the next time you can say that C in is C out from the previous addition. Right, so that's it. So this is how you can simplify your task. You can so now if you want to say make a 7-bit adder, 8-bit adder, you can write 8 here, and of course you need to define this as a 9-bit variable, and this as in two 8-bit input variables, right? So but in this case we are only uh, making a 4-bit adder, so let's redo reset the values, and right, and this be 4. Okay, so now you just need to save this and now simulate this. Right, so as you can see, there are no errors. So we have already made the test bench. So now we can simply just click on this behavioral model to simulate behavioral model to simulate it, and we have some errors. So maybe we need to first simulate the test bench as well. Again, test bench, simulate the test bench again. So let's click on this and right click. Now you need to, yeah, here we are. You can, so those errors are because we simulated or we ran the behavioral check of the module, but we did not run the behavioral check of the test bench after we changed the module. So we need to run the behavioral check of both test bench and the module if we make any changes in the module, right? So this is how we can make a 4-bit binary adder, right?